There is a train tunnel under Victoria Harbor right now. A cargo ship is crossing above it. The ship's crew has no idea. The passengers on the train have no ear. And until I looked into this properly, I had no idea either. What I want to explain is how that tunnel got there, because the way it was built is one of the most technically demanding things I have ever read about. And I think once you understand the actual numbers and the actual problems they hit, you will feel the same way. Let me start with the basic problem. Hong Kong's East Rail Line had been stuck at Hung Hom Station for 43 years. Every morning, around 500,000 people would arrive at the edge of the harbor and stop. The eastern part of Hong Kong was essentially disconnected from the island. To fix that, engineers needed to cross Victoria Harbor. The harbor is 1.4 kilometers wide at that point. That is not a small gap. And here is the part that surprised me. There were already 5 tunnels under that harbor before this project even began. 5. So the 6th tunnel had to thread through a gap of roughly 90 meters between existing structures. 90 meters sounds like a lot until you are moving 23,000 tons of concrete through it in the dark. Now, the method they chose is called immersed tube tunneling. I want to explain this clearly because I think most people imagine tunnels being drilled through the ground. This one was not. It was built on land, first, then floated into the harbor, then sunk. That is the core idea. Build it dry, float it wet, sink it permanently. So where do you build 11 giant concrete tunnel sections on land, next to a working harbor? They used a quarry, an actual rock quarry. They converted it into a casting basin. Workers built the concrete boxes there, one by one, over 30 months. Each section is enormous, 23,000 tons each. To give you a sense of scale, the rebar cage inside was so dense that workers had to physically climb through it just to move around. But before a single drop of concrete could go in, the casting bed had to be perfectly flat. When they measured it, the bed was 340 millimeters out of level across its length. That is more than 13 inches of slope. Cast the tunnel on that surface, and the sections would never line up when placed on the harbor floor. So they grouted the low spots. They filled them, checked again, filled again. The final tolerance achieved was 5 millimeters flat across 160 meters. That is impressive to me. 5 millimeters across the length of an airport runway is essentially nothing. Then concrete goes in, not in stages. In one continuous 36-hour pour per section. The concrete grade is C45, which is a high-strength mix. And here is why the non-stop pouring matters. If you stop and restart, you get what engineers call a cold joint. That is a weak seam where the old concrete and new concrete meet, but do not fully bond. In a tunnel under the sea, a cold joint is a potential water path. So they run the pour without stopping. Thermal sensors inside the walls monitor the heat as the concrete sets. Too hot in one spot, too cool in another, and the integrity of the section is at risk. Once casting is done, Each section gets waterproofed. Every single millimeter is inspected, because one small gap in that membrane is enough for harbor water to enter a tunnel full of passengers in minutes. This is confirmed. The pressure at 30 meters depth is around 3 bars. That is 3 times normal atmospheric pressure pushing against every surface. When all 11 sections are cast, the quarry wall comes down. Harbor water floods in, and 23,000 tons of concrete floats. That part genuinely surprised me when I first understood it. Concrete floats. Because the section is hollow and sealed, it displaces enough water to rise. The quarry becomes a dock. The tunnel sections are now vessels. Then comes the part that I find hardest to fully picture. Moving one of these things through Victoria Harbor at night. The harbor shipping lane is 200 meters wide at the tightest crossing point. Each tunnel element is 18 meters wide. 5 tugs control it. GPS towers on the roof of the floating section allow engineers to track its position to within a centimeter at night. In a live shipping lane, a cargo ship on the left does not know it is passing 23,000 tons of future railway tunnel. Before each section can be placed, a trench has to be cut through 30 meters of harbor silt. The bottom of that trench must be flat to within 100 millimeters. Get it wrong, and the tunnel section lands at an angle and stays there. To ensure flatness, divers and specialist equipment screed a gravel bed on the trench floor. The tolerance for that gravel bed is 20 millimeters. 20 millimeters for something that will carry 23,000 tons above it. Marine police close 200 meters of the world's busiest shipping lane for 48 hours per element to allow this work. Then, the immersion pontoons grip the section. Ballast tanks fill slowly with water. The section descends 30 meters down. At the bottom, it meets the previously placed section. Between the 2 concrete faces sits a rubber seal called a Gina seal. As the new section is pressed against the old one by the weight of water above, that seal compresses. The compression is the watertight joint. No bolts through the harbor floor. Just pressure doing the sealing. But during Element 4, a cargo ship anchor dragged across the gravel bed that had just been scraped flat. It disturbed 180 millimeters of gravel. That is 9 times the tolerance. Element 4 cannot go down on a damaged bed. Engineers hold it at 15 meters depth for 4 days. 4 days. The section is suspended mid-water while divers go back to resurface the bed. When it is confirmed flat again, descent resumes. Element 4 lands. The joint space between elements is pumped dry from the inside. Then a second seal is installed from the dry side. 2 seals now stand between the passengers and the harbor. What I understand from that part is that the system is designed with redundancy. 1 seal compresses from outside pressure. A second seal is added manually from inside. If one ever fails partially, the other holds. Now, the immersed tube tunnel is only one part of this project. The tunnel also needs to connect to land on both sides. And on the land side, the method changes completely. 7 tunnel boring machines, 4 separate drives. The geology changes between each drive and every machine has to adapt. The TBMs work inside pressurized slurry. That means the cutting face is held up by pressurized liquid to stop the ground collapsing, while the machine drills forward. One TBM is working just 3 meters away from the harbor water table at certain points. That is close enough that a miscalculation in pressure could allow water in. There are around 400 old building foundation piles directly in the path of the tunnel drives. Some of these have to be broken through, others have to be navigated around. There is no third option. And the lining ring, the concrete ring that lines the tunnel immediately behind the cutter head, must go in before the machine moves forward. If the ring is not in place, the ground above can collapse. That is the basic rule. No ring, no forward movement. One TBM jams 400 meters in. An uncharted concrete raft, something that was never on any record or map, completely stops the cutter head. Engineers probe from street level to confirm the raft's position, then grout around it from above. The machine resumes after 8 days. 8 days underground, stopped, with the ground holding above. At certain points, rock has to be blasted. In Lieve, Hong Kong, the charges are calculated specifically to stay within limits that protect buildings just 10 meters above. 200 sensors are placed on surrounding structures. If any single sensor reads above the limit during a blast, all blasting stops immediately. No exceptions. This is confirmed as the operating rule for this project. There is also a 300-meter open excavation station box with 50-year-old apartment buildings on all 4 sides. Diaphragm walls, concrete walls poured into the ground before digging begins. Hold the surrounding earth in place so the buildings do not shift as the hole is dug. What surprised me here is that during this excavation, workers hit a 900-year-old Song Dynasty archaeological site. Wells, ancient structures. 11 months of work stopped. 20 billion in delay costs recorded. The station layout was then redesigned around those wells. The structural grid shifted 3 meters sideways. To me, that says something clear. Engineering deferred to history. The well won. Then comes what I think is the most serious problem in the entire project. An inspector finds a disconnected rebar coupler buried inside a live station wall at Hung Home. He finds 1,900 more. Rebar couplers are the threaded connections that join steel bars end to end inside a concrete wall. They are critical. Without them, the bars are not connected. The wall has less strength than designed. In this case, short bars had been dropped into wet concrete without being connected to the couplers. The concrete then poured over them. The bars are buried, but not doing their job. 8.9% of the connection system in those walls is missing, and those walls are currently carrying live train loads. Everything stops. All pours halt. Every wall on the project goes under investigation. The question then is how to fix steel inside hardened concrete. The answer is brutal but logical. You do not fix the concrete. You bypass it. A steel frame is installed to carry the load that the defective walls were supposed to carry. Every train above those walls now runs its load through new steel beams, not through the defective concrete. To install that frame, 650,000 tons of rock are removed from the station excavation, working entirely at night. Last train stops. Work begins. By 5 a.m., the rock must be clear. Then 5,000 tons of steel are welded underground in the confined remedial space. No crane, no sky above, just heat, confined space, and steel. The inquiry confirms the fix is structurally safe. Work resumes. 4 years of schedule are gone. Below Admiralty, engineers are digging below a 40-year-old live rail line, the Island Line. Trains run every 3 minutes above the workers. At one point, settlement of the Island Line tunnel reaches 22 millimeters. The limit is 20 millimeters. 2 millimeters over. Everything stops. Steel props are hand-tightened under the tunnel in under 40 minutes after the last train runs. Engineers work overnight to recalculate. Settlement stabilizes at 23 millimeters, 1 millimeter over limit. But the calculation confirms it is safe to continue. The excavation resumes under the moving trains above. What I find striking about this project is that multiple world-first problems appear in the same job. The harbor tunnel required a custom seal. The standard Gina seal is not rated for 30 millimeters of tidal movement at 3 bars of pressure for 100 years. That is the actual load case for this tunnel because the harbor bottom moves slightly with every tide cycle. Engineers designed a new Omega profile seal, tested at 2.5 times operating pressure, rated for 30 millimeters of movement for 100 years. It is now a new engineering standard. Once the concrete and steel are all in place, the systems have to be tested. The signaling system controls every train automatically. 8 months of reconfiguration, certified in 2022. Then, the signaling test reveals that platform screen doors and trains are not communicating correctly yet. That gets fixed. A 72-hour live electrical test follows. 27,500 volts energized across 5,000 meters of tunnel. Then 12 months of empty trains running daily, every system stressed on purpose, every fault caught before a passenger boards. And even after opening, monitoring continues. 23 groundwater sensors are placed under the harbor. Any rise above baseline triggers a dive inspection within 24 hours. Sensors 7 and 8 are rising 0.4 millimeters daily. The limit is 0.5. The seal is confirmed intact, but the cause of the rise is not yet known. A container ship crossed above the tunnel today. Its propeller wash compressed the Gina seals below it. The seals held. They are designed for that, but the engineers are watching. So for me, the main thing I take from all of this is simple. The hardest part of building this tunnel was not the concrete. It was not the steel. It was not even the geology. It was the fact that almost everything had to happen while everything else was already operating. Trains running above, ships crossing above, buildings standing beside, ancient wells beneath. And through all of it, the tunnel had to go in anyway. That is what I understand now.